So my name's Trent Hare. I'm coming from USGS. I'm in Flagstaff, Arizona. So it's not too early, but afternoon to everybody. Um, this is more of a fun talk. It's just talking about how we go about generating base maps for helping to land the last rovers that we've supported over the years. So the original title, I gave this to Phosphor-G in Italy this year and in or 2022. And so I've basically just recycled this one for this group just to show you kind of what goes into making all these nice base maps that we're able to map on. This is a little bit different because we're talking about how to make sure that there's no interior errors within the base map generation. And so let's go forward. So USGS has been around. We're actually celebrating our 60-year anniversary this year, which is kind of hard to fathom, but we've been supporting lunar geologic mapping and lunar landing site characterization, and now Mars, of course. And we actually are having an analog meeting just today talking about training astronauts in the field and techniques for that. So we still do a lot of that. We're supported by NASA to support community goals. So just to get over a little more of those standards that we work with, and this is not just us, this is a community effort. We directly support things like planetary geodesy. We support just housing the planetary nomenclature, so naming of the features, which is very critical for geologic mapping. Generally, most geologic mappers will come into a map understanding that, hey, I've got a new thing that's really important for my science to discuss. I don't want to call it crater A or crater B. So let's go ahead and ask the IAU for a name. And that's an international working group, not just the US. So that goes across all boundaries. And then we support geologic mapping. And what do we mean by that? We support NASA-funded publication of geologic maps. And we've been funded for quite a bit of time consistently to support that. And so we use USGS standards for mapping, for publication, for cartography, and then we also use appropriate metadata for those maps. That includes symbology, making sure that everything's kind of up to par. It goes through kind of a rigorous review, and then they're published. So it's a very long-term process to go from actually proposing to do a map to the publication of the map. Of course, the mapping can take 2 to 3 years or longer, and then the publication can add on to that because of all the review processes and the cartography and the finalization that goes into that. So it's interesting to see that we're trying to figure out how to make this more open across just outside of the US. So, sharing templates, sharing symbology, sharing tricks like MAPI and QGIS and map projections and tools is going to be important so that we can keep these maps consistent. Geologic maps are supposed to be used regardless of what planet you're on. You're not supposed to have to, if you know geology, you're supposed to be able to use it from any planet. So having those standards is really important. We do support PDS, so data publication and data archiving. We actually also have a working group called MapSet that supports cartography and mapping recommendations. And then something that I've been involved with for most of my career is web mapping standards, working with the Open Geospatial Consortium and GIS standards. So GeoTIFF and GeoPackage and IU projections. And now we're supporting a new thing called STACK, which is for individual images. And lastly, being part of the photogrammetry group, which is what I'm talking about today, we do support the camera sensor model working group. Let's see. So just as my kind of my stance, I like to talk to this slide every time I do a presentation. I really want people to understand that we should all make the data the focus. Obviously, that helps support any science, but it also helps support future scientists. So it's not just the process, it's also the understanding to make the data open, making the data available, making it well explained what is it good for. So understanding that not only are you making a map, but how do I make that understandable, or how do I make that so that people can know where to use it or what it's good for? So one of the things that we've been promoting in the community is understanding that analysis ready products are critical. A lot of data in the planetary community is just frankly hard to use. So trying to get the experts, and that's usually the mission team or the instrument teams, to generate analysis ready products is critical, so that we can drag these into QGIS, and so that we can drag them into a viewer or a remote sensing package for spectral analysis or for mapping on. So if every geologic mapper has to go out and make their own bases, that's essentially not a waste of resources, but it's definitely putting the burden on the geologist, and some place where hopefully we can help, make these bases available, make them ready, and make them mappable right away without having to worry about if it works in QGIS or not. So supporting open standards, supporting open source like QGIS is widely beneficial. You'll notice that, QGIS is an Earth-centric application, which is why we're seeing some of those errors that we're working through and working with the QGIS team on trying to fix. So I do recommend, when at all possible, adapting standards is almost always better than inventing. So, and what's a good example of that? We had to write MAPI to support QGIS, but we didn't, there was no, you didn't have to go through and do all the hard work and years of technology that was put into QGIS. And then, making data the focus. Whenever you use data, make sure that it's well credited. And then also, if you're a data provider, make sure it has good metadata so people can credit you. So the community is getting ready and supporting DOIs, supporting persistent identifiers so you can find it, supporting good metadata. And we're all getting better at this as we go along. But the worst thing we could do as users of data is to not credit it, such that the original person doesn't get the credit that's deserved. So let's jump into this mapping. That was kind of my introduction. This is probably getting to be a little bit of an older slide, but it's showing kind of the progression of science and missions that are heading to Mars. And you can see that we're currently in this orbiter lander phase. There's going to be some missions going to Phobos and Deimos that I think JAXA has the next mission to Phobos. There's lots of different countries doing these landers and orbiters, and drones now. We actually have the first drone on Mars, which is amazing. The Ingenuity drone, which has been flying around for the last, I don't know, several months, almost a year maybe. So let's jump into how do we support these. So back in the late 90s, one of the first landing site support that I was involved with was Mars Pathfinder. And let's just go through how this number one was supported and how it was landed. These were the data sets that we were using at the time. This is mock data, which is, you can see is very sparse. It's narrow. There's not a lot of data. You can see there's a lot of spacecraft jitter in the orbital path. So this is a stereo pair, and you collect the stereo by doing intersections in 3D onto the surface. And you can see that there's a lot of issues with trying to use this to land on. This was actually used for analysis for the MER landers. And how could we get away with being so rough and kind of allowing these errors? This is a smooth version of trying to correct that jitter. This is all software based. It's not analytical. So you have to be careful when you see jitter. Anyways, so that was one of the first, and the reason why we could get away with that with such kind of a rough topographic map was because of the way that the Mars the MER landers landed and Pathfinder landed, and they used this technology that would basically open up a parachute. There was radar grounding to understand how high it was. There's back shell firing, and then it would slow down and drop off a giant set of inflated balloons, and then those balloons would deflate and the rover would pop out. So let's see how big that is. So we could get away with kind of bouldery areas. You could get not necessarily bouldery areas, but you couldn't still land on steep areas. You couldn't land on really rocky areas. So there was a lot of mapping done for boulder counting, for craters. So we would get a rough idea for the landing site, and then you would just drop down this giant airbag and hope for the best. And it worked. And it was pretty amazing technology at the time, and kind of driven by the fact that we didn't have the data to really do this correctly, and the technology. So here's actually the Mars Pathfinder after it landed. I think you can see some of the airbags have been deflated over here on the right. And you can see the rover. I think this is where it actually ended up stopping, or potentially a little further. But it was a pretty small rover. And you can see the rover size at 10.6 kilograms. And let's see a distinction between then and now. So here's our little Pathfinder rover. Here's the MER rovers. And here's what we're sending to Mars now. And this is analogous to the Mars 2020 and the Mars Science Laboratory size. So we can't use airbags for that size. Airbags are just not good enough. No matter how strong the airbag is, you can't land something this large in an airbag. So what do you need to do? You actually have to use what's called a sky crane. And the sky crane has the retro rockets. It lowers down the rover releases its wheels, and then it lands itself, and the back shell or this retro rocket detaches and it flies away. So what we're doing now is, because we have the data and because we have the methodology and the technology to do this, we can actually now nearly autonomously figure out where it is safe to land, fly around quickly. You only have seconds really to fly around, figure out where to land, and then land the rover. And so this is called the sky crane technique, pioneered by the Curiosity rover. And so how can we do this thing called terrain relative navigation? Essentially, like a drone, there's no way to actually control this as it's landing. The delay from Earth to Mars is such that it's like a 20-minute delay. There's no way to do real-time landing. So this all has to happen on the spacecraft. So what happens is, as the whole spacecraft descends, the parachute opens, it actually has instrumentation on board the spacecraft, figures out where it is based on an image mosaic on board the spacecraft. It does image matching techniques, and then it can actually fly itself to a safe landing site, release the rover, and land the rover. And so we'll see that in a second. So what do we need to do to be able to enable terrain relative navigation? And again, automatic image matching on board the spacecraft using mosaics built here. So that's what our job was. Our job was to generate the most undistorted image that we could possibly make using existing data, such that when the spacecraft hit the atmosphere, it could take images and then do automatic image matching and find out where it is, and then find it, and then actually locate a safe place to land. So I'm going to skip over these, but these are some, I've already uploaded this presentation, but these are some of the reasons for the Mars 2020 mission. You can see the geologic context, looking for in situ astrobiology. It's a nice river delta, and so we're hoping to find past life. Terrain hazards considered: rocks, very dangerous. High slopes are always bad. You're never going to want to try to land on a tilt. So part of the analysis was not only finding an image for the spacecraft to match to, but also hazards based on DEMs or digital elevation models. We wanted to make sure that the thruster plume interaction was safe on any given slope. So that meant it had to be, there couldn't be too much dust or dunes. And then there has to be enough space where you can actually land that large of a spacecraft. So a 2.5 kilometer baseline needed to be found. So, and also it's not flying around forever. So it has to be able to find itself a safe landing site fairly quickly, or it'll run out of fuel. So this is the site that was chosen, Jezero Crater. Here's actually a geologic map that was done prior to landing by Sun et al. And here's the link for that. Again, this link will be provided in the slides. And you can download this GIS, pop it into QGIS. You can download the image base map that was used at the time. This was done on a base map previous to our final base map for the actual landing. And then also there's interactive maps at that site if you just want to browse the data without having to download it. So what did we have to do? What did we need to do in terms of data? We had to gather everything that we had available from NASA and ESA. That includes the HRSC data, the high-rise data, which is high resolution, 25 centimeter per pixel, the context data that was flown alongside the high-rise data at 6 meter per pixel. So the actual image that went on the spacecraft for image location, for image matching, was the CTX mosaic at 6 meter per pixel. You didn't have to go down to high resolution, because if you think about it, it's taking pictures from high up while it's landing with the parachute. And so we don't need to have the highest resolution data available. You just need a medium resolution for it to do quick image matching. And then we used the high rise, which was highly matched to it, to the scientist gathered all the information from that for a hazard map. So there's basically there was the image map for matching on the spacecraft, the CTX, and there was a hazard map, which is basically safe, not safe. And this was used in concert on the autonomous methods to find itself a safe landing site. So the orthomosaic was loaded on board the Mars 2020. It's considered truth, and that was again used to match. And so some of the requirements that we had to be able to have this was the most strenuous requirements we've ever had to do, and only the MSL rover is going to kind of up the ante for the accuracy. So our absolute vertical error had to be less than 20 meters, and that was with respect to the HRSC, the new version, the level 5 digital model. And then CTX to CTX, so we did multiple stereo pairs crossing the whole area. Those had to be within a 99 percentile within 6 meters. Horizontally co-registered within 60 meters, or the 99 percentile relative to HRSC, so horizontal. And then the CTX images had to be co-registered within 6 meters. So that's basically pixel level registration, pixel level errors. We were very concerned about distortions in the images. So no warping, no rotation. That was very hard to take care of in the automatic matching. This base map, the CTX mosaic for TRN, again, probably the most error-free mosaic we've ever generated, is available at this DOI link. For high rise, again, this was used it wasn't used for on board the instrument, but it was used for mapping the hazards. So basically the pixels had to be extremely well aligned. It doesn't help if you have one mosaic and another mosaic that doesn't line up very well. And in planetary, we just take that for granted. There's always going to be horizontal errors. There's always going to be, and even though these two bases are highly registered to each other, it doesn't mean that we actually know the precise location on Mars. So we still have absolute accuracies over the whole of Mars that doesn't approach the error, the amount of precision and accuracy we were able to glean from these two mosaics that were tied together. But globally, we still have very unknowns, very unsure, up to almost the 100-meter level. And so, you know, that's another reason why we can't pinpoint land a rover, is because we actually don't know where these mosaics fit on the surface perfectly. But once you locate yourself on the inside the image, then you know where you are. And so that's, again, a key distinction between when you're using GPS on Earth, you pretty much know where you are on the body. On Mars, you kind of know where you are, but you know where you are within an image once you can locate yourself in that image. So this is kind of the slide that I was trying to get to quickly at the Phosphor-G meeting, but it really is a highlight of all the open source packages we were able to use for this process. And you can see that about 85% of the software we used was completely open source. So let me run down this. We had GDAL and Proj kind of backing up the whole map projection and image formatting side on the left side. We are able to use the existing capabilities within ISIS, the USGS ISIS package, and JPL SPICE toolkit to locate our images. We actually jumped into a commercial application called SocketSet to generate our DEMs. So this was how you get a stereo pair, one nadir, one off nadir, and you can generate the elevation model from that. And that was actually an iterative process with AIM Stereo Pipeline. So we generate the DEM, we generate the initial bundle adjustment using BAE's SocketSet, and then we actually align everything within ASP, and we do this multiple times until we're happy with the results, or the getting that data down to that 99 percentile that we needed to fit the requirements of the mission. NASA ASP is extremely powerful open source package that actually will compete with commercial applications like SocketSet. And yeah, if you haven't used it, amazing tool, well worth looking at if you're interested in topography. And then we actually did use QGIS and the Saga plugin for QGIS to do things like normalized cross correlation, so image to image matching before we actually went to the spacecraft, such that we could understand, okay, what are the errors in between the images? So you take one ortho image, you take the next ortho image, and you do some image correlations, and you get those errors out. So we did a lot of that with a package called IMCore that's built into Saga that was plugged into QGIS. So all these things went directly into supporting these base maps. And just to give you a sense of the registration, this is a blink. If you can see that, it's blinking between the CTX at 6 meter and the HiRISE at 25 centimeter. And you can see subtle differences. Mostly those are probably shadows or just texture differences. But this was the key. We had to have these as perfectly aligned as possible. And we were able to meet that as much as we could. And we're limited by the data. We're limited by the spacecraft, any optical distortions that we didn't resolve on the spacecraft, any SPICE issues we had. Our partners at JPL really helped us beat down errors from timing. So there were so many kind of difficult steps to make this base map. And in closing, we landed safely using that terrain relative navigation. Here's a video I'm going to show over the last couple minutes, and I hope you can hear the audio. If you can't, let me know and we'll just cut it off, but hopefully the video will work. And I'll try to talk through this a little bit, although there is a good voiceover for this video. It's a 3-minute video, so.
The navigation has confirmed that the parachute has deployed and we're seeing significant deceleration in the velocity.
So take a look at the bottom panel. You can see how what stage you're at. So these are actually a bunch of cameras on the spacecraft. They've just dropped the shell.
First look at the surface. Current velocity is 145 meters per second and an altitude of about 9.5 kilometers above the surface.
So right now the radar's seeing how high it is and the image matching is starting. And if you're used to Jezero, you'll start recognizing features.
3.3 meters per second, altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers of the surface.
So radar lock, it knows how high it is.
On the parachute, we're commenting on the initialization of terrain relative navigation and subsequently the timing of the landing engine. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
So she just said they initialized terrain relative navigation.
We have confirmation that the land vision system has produced a valid solution in part of terrain relative navigation.
So it already matched.
We have timing of the landing engine.
So now it's looking for a safe place to land, really. It knows where it is. It found itself.
83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
You're on safety Bravo.
Yeah.
So you can see that pretty exciting, but that's fun video to watch. It's pretty amazing that they had all these cameras rolling while we were landing, going up to the parachute, going back down. But you can see that the image matching didn't take that long. And then from then on, it was basically locating itself using that image. Once it knew where it was, it probably switches over to the hazard map and finds itself a safe place to land. And I will say that the next generation, we're actually going to be a little bit tougher on ourselves. It's going to be a little bit more precise. I guess what that means is that they're going to be able to land in a tighter area. So the reason we want to do that is that we want to go to these areas that are rocky and hard to get to, so that you can find the interesting geology. The previous missions that used airbags, we basically called them parking lots because we had to land in a really safe space. And the next TRN, you'll notice that there'll probably be terrain relative navigations on the moon. And here's where we're talking about for the Apollo or for the Artemis mission landing sites. And I'm assuming, 2 or 3 of these will be chosen eventually, and we'll go there with several missions. And that's it. Thank you.
Thank you, Trent. This was a fantastic presentation. I see there has been also appreciations between also our attendees. There's a question. So the onboard imager doing the image matching while descending towards the zero was 2D. There was not a 3D element in the image matching before landing, right? Or there was a stereo matching of some sort of.
No, it was, well, so they had the radar, right? So they know how high they are, but it was complete 100% 2D matching to find out. And it's, I'm not sure, getting our hands on that image matching code. I don't know if that's been open sourced yet. I assume it will be eventually, but it's just using fairly simple methods to do image matching, and yeah, completely 2D. But again, the spacecraft knows how high it is.
Thank you. Are there any more questions related to the talk? If not, we can move to the general Q&A for the day. Yeah, so another question is that like the Sky Crane, does it contain some scientific instrumentation like payloads, or to make some size of opportunity, or is just a device for deploying the rover? You are muted.
Oh, what was the first part of that question?
So does the Sky Crane have any type of payload for science of opportunity, or is just a way to deploy the rover?
Besides the instrumentation and the video cameras, to do the image matching on board, it is yeah, mostly just a technical and engineering. And it will basically, once it releases the rover, once it's landed, it flies away and just basically dies. So there's not really any instrumentation besides getting it landed.
Okay. I guess we thank you, Trent. I mean, this was a very nice closure.
Well, and I think the fun
well,
part
another
is that
question.
definitely check out the data. It's all available. And you can use it as a good mapping site. There's a lot of highly correlated data now, the DEMs and orthos and all the data that is released with that data is just fun to visualize. The geologic map's great by Sun. There's a lot of science going on and a lot of rover data, of course, happening.
Okay, we have one last question, then we need to close. So does the rover use image matching also when it's moving? I guess the answer is yes.
Once it's landed, it has a whole different suite of instrumentation. It has several cameras on board the rover that it'll deploy, including stereo. And so it will do its own 3D using the various hazard cams, nav cams, and also it'll have the science team will be generating DEMs for safe roving. So yeah, once it's landed, all the other instrumentation used for getting it landed are basically gone, and the rover switches over to all the instrumentation on board, including releasing the little drone Ingenuity helicopter. It released that and it was able to fly away.
Thank you, Trent. It was really, really beautiful presentation. So thank you for being here also this year. We really
and I see one last question about
yeah.
So AIM stereo pipeline does allow anybody to generate their own DEMs. It is quite a challenge. There are folks who are generating these DEMs from the team, from other, and I highly recommend, if it's available from the PDS or made available from an instrument team, definitely use that. But it's well worth learning ASP and all the quirks that go along with it to make your own. Just be careful. There's a pretty steep learning curve, but it's well worth looking at and a good technology to use. One last statement I'll say is that if you're a little more patient, we have a project here to generate as much CTX. It's mass produced, so they're not they're not perfectly aligned like this set, but they used AIM stereo pipeline to do as much CTX DMs as we could find, and those will be released probably within the next few months.